Good day, so I'm Dr. T and welcome to my table. So today I'm working on a couple of problems and I've got a little bit of a long one over here that should be an interesting one. Okay, so the problem as I've written it, hopefully I haven't butchered up the grammar on this one. If you wish to heat 6.25 liters of water from 18.2 degrees Celsius to 95 degrees Celsius by dropping rocks heated in a fire into the water, what mass of hot rocks do you need to add to the water? Okay, that's fairly straightforward, but I need to know a lot of background. By the way, this would be how prehistoric peoples would heat water. You can't put, say a skin worth of water over the fire because the skin would burn. So you heat rocks in the fire and then you dump the rocks into the water that's in your animal skin. Now, I need some information. So, assume the rocks after heating the fire and cooling a bit while you move them are 450 degrees Celsius when they hit the water. And right now, as the author of the question, I'm going to edit that question slightly and put a decimal point there, which was supposed to have been there. So, otherwise it would have been 2 Sig Figs. So, moving on. Okay, so the rocks are 450 degrees water. You know what? Why don't I just draw a picture? Sometimes drawing a picture is the best bet. So I've got my skin of water. We'll make it a deer skin. Okay, it's terrible looking deer skin. Okay, so I've got the water. I've got my rocks. Okay, the rocks are starting out. So temperature initial equals 450 degrees C. The water, temperature initial is 18.2 degrees Celsius. Temperature final equals 95.0 degrees C. By the way, when we have a temperature final, it's going to be the temperature final for everything in the space, because if I drop the rocks into the water, they're going to cool off until they match the temperature of the water. So T final for everybody is going to be the same. Now, obviously, then the whole thing will start cooling off, the insulating property of this deer hide. It's not part of the question, so we're going to kind of ignore it, but, it would be a thing. Okay, let's see. Specific heat of the water is 4.184 joules. And the way this is written is grams Kelvin. That means with those little superscript -1s, that means it's in the denominator. By the way, in this case, because we're working with delta T's, we can use Kelvin and Celsius interchangeably as long as the T initial and T final match. Normally you can't do this, but this is one of the few cases where you can do this. So that's there. Specific heat. I need to know the specific heat of the rocks. Okay, so we're assuming they're limestone, because obviously different rocks, different specific heat. That's going to be 0.909, and it's the same units. Okay, so what we're going to do on this one is we'll set up a calorimeter equation. So this is going to be mass water plus specific heat water plus, sorry, loud car, plus delta T water equals mass rock times, that's not a plus, that's a time sign. Those are time signs, don't be silly, Dr. T. Okay. CS rock and delta T rock. So, by the way, we do need to put a -1 literally anywhere in this equation. That's because this is the hot side, that's the cold side. So on this side, this is an exothermic process, where on this side it's an endothermic process. So we just have to times a -1. It literally does not matter where. You'll see a lot of them will put the -1 on the delta T. So I'll make it a negative delta T. Or they'll say initial minus final. I find that so confusing that I just don't use it. Okay, let's see. Oh, we have one more piece of information. We don't have mass water, we have volume of water. Okay, so water, 18.2. So if I wanted lots of Sig Figs, I could go look up the density of water. With 3 Sig Figs, it's going to be pretty close to 1 gram per milliliter. So I'm going to assume it's 1 gram per liter. If I wanted more precision, well, that would be another question. So I'm going to have 6.25 liters. That's going to equal 6,250 milliliters, and that would be, if it's water, with our assumption, 6,250 grams water. There's no squiggle there. Okay, so I'm going to have 6,250 grams. No decimal point in that case, because in this case, other than that typo, that's only 3 sig figs. Okay, so now 4.184 joules per gram Kelvin. The grams cancel, times parentheses 95.0 degrees C minus 18.2 degrees C. I grab a calculator for that. So 95 minus 18.2 gives me 76.8. It's 76.8, yeah, it was. And in this case, and in this case only, because this is a delta T, I can cancel those two. Normally you cannot do that. But because this is a delta T, I can. And I'm going to regret using this much paper because I have to do more. Okay, so in this case, the mass of the rock, I don't know. The specific heat of the rock, that's going to be I don't know grams. 909 joules per gram degrees C, or K, whichever you want, times, in this case, it is going to be 95.0 minus 450. Okay, so that's going to give me 355. See, those are going to cancel, and I still have that minus 1. Okay, I just bumped the paper. Let's see if it's still on the screen. Okay. Now, basically, this is just algebra. This is nothing but really annoying algebra. So I'm just going to take this whole side right over here, and I'm going to do 6025, shoo the little bug away, times 4.184 times 76.8. This equals, big number. This is going to equal 2.008. That's 4 sig figs. I'm only working with 3, but I'm not done yet, so I'm not going to do my final round. But I don't really want to write that whole number down anyways, and that was times 10 to the 6th, which on some brands of calculators, a capital E means times 10 to the 6th. Okay, so that is going to equal, I don't know, times 355 times 0.909 gives me 322.7. And let's look at the units here. So over here, this case, these guys are joules, because that's the only thing that didn't cancel. Over here, this is going to be joules per gram, because remember, that's still grams. It just hasn't canceled. Okay, so now I'm going to divide both sides by 322.7 joules per gram. So that means that whole thing cancels over there. Where on this side, I have 322.7 joules per gram. The joules cancel. The gram is going to flop to the top, and I'm going to get my answer. So now I take 2.00832. Trying to remember the way to pull that one up. The 89 will do that. The 83 won't. Probably doesn't hurt, or doesn't help that I'm using a 20-year-old calculator. But hey, this worked good in high school. It's still good. Okay, I'm going to do the second EE button. You want to actually use the scientific notation in your calculator just because it can do some kooky things if it doesn't realize it's scientific notation and thinks it's something else, especially if it's in a denominator. This isn't, but especially if it is. Okay, so this gives me 6.2235 grams equals question mark, which I know is in grams too, which is good. Let's do some Sig Figs. This is going to be, decimal point goes there, not there. That's a comma. Typically, we don't actually use commas. They get too confused with decimal points, especially if you're going across the pond, because there's a lot of European systems which will switch the meaning of the comma and the decimal point. Okay, so this is going to be 6.22 kilograms, because I'm just going to switch this over to 6.22 kilograms of rock. And that is my answer. And by the way, the reason I can switch that to kilograms at will is because what mass? I never said what unit. So typically speaking, at least in my classes, if I don't specify the unit, you're allowed to use any unit you want for an answer. Obviously, different instructors have different opinions, but hey, if I didn't say it, then you get to make that up. Now, if you give that to me in, say, slugs, you are going to get an odd look from me. And you better be right. But with that said, feel free to answer in slugs if you really want to. I don't know why. And have a wonderful day.